Ever stop to think about how much we rely on simulations these days? I'm not
Mm.
talking about like video games or anything, but actual science,
Mm.
like climate change or even, the universe itself.
Oh, absolutely. Yeah. Simulations have become so crucial, especially in physics.
Right. Because let's face it, trying to recreate the Big Bang in a lab is a tad bit impractical, wouldn't you say?
It's true. Real world experiments on that scale. Yeah. Pretty much impossible.
Exactly. And that leads us perfectly to today's deep dive. We're delving into a tool that's causing quite a buzz in the physics world. It's called FeynMG, and it's all about making life a bit easier for physicists grappling with some of the universe's biggest mysteries.
FeynMG is interesting because it's specifically designed to work with what we call modified gravity theories. So these theories, they're basically trying to address some of the things we still don't quite get about gravity, like those areas where Einstein's general relativity, you know, might not give us the complete picture.
So when we say like shortcomings, we're talking about things like dark matter, dark energy, that
Yeah.
sort of
Yeah.
thing, right? Those cosmic puzzles that
Yeah.
seem to throw a wrench in our current understanding of physics.
Exactly. Those are the big ones. These phenomena, they really make us wonder if gravity might behave differently on those massive cosmic scales than we currently think. And that's where these modified gravity theories come into play, trying to fill in those gaps.
Okay, so how does this FeynMG thing actually fit into all of this? Because from what I'm gathering from this paper, it's not like some groundbreaking physics theory in itself, right? It's more like a tool, a software. Am I right?
You got it. FeynMG is basically a piece of code, and it's written in Mathematica, which is this super powerful computational language that physicists use all the time. Imagine like a mega-powered calculator. Only instead of just crunching numbers, it actually helps physicists model these crazy complex physical systems and actually test out their ideas.
Ah, so it's like giving physicists a souped-up toolbox to play with, especially when it comes to these modified gravity theories, which I'm guessing involves some pretty intense math.
Oh, absolutely. Modified gravity theories, they're inherently more complex, so the math gets pretty wild pretty quickly. And that's where FeynMG comes in. It really helps streamline the whole process, allowing physicists to explore different scenarios, tweak things here and there, and see how these modified theories might actually play out.
And speed is key here, right?
Hmm.
Because time is precious, even for physicists trying to unlock the secrets of the universe.
Oh, 100%. Time is always of the essence. With FeynMG, physicists can actually test out their ideas way faster, which means they can explore a wider range of possibilities and see if a particular modified gravity theory holds any water and do it all much quicker.
So less time hunched over whiteboards scribbling equations
Yeah.
and more time actually, thinking big picture stuff.
Precisely. It frees up their mental bandwidth for the really creative, insightful stuff.
Now, this paper we're looking at, it delves into some pretty specific concepts related to modified gravity, like Brans-Dicke theory and something called the Einstein frame, which I have to say sounds a little bit like a comic book thing, doesn't it?
It does have a certain ring to it.
It does. So could you break those down for us a little? What are we talking about here?
Okay, so let's start with Brans-Dicke theory. Now, if you remember, Einstein's general relativity tells us that gravity is essentially a consequence of the curvature of spacetime, which is caused by mass and energy. A classic way to visualize it is to think of like a bowling ball on a trampoline.
Right, the bowling ball being, say, a planet or a star, and the trampoline representing space-time.
Exactly. That's a good way to picture it. Now, Brans-Dicke theory, it comes in and says, well, what if that curvature, that give in spacetime, what if it's not always constant? It proposes that spacetime's flexibility could actually be influenced by other factors, which adds this whole other layer of complexity to it.
So it's like saying the trampoline itself is made of a different material in Brans-Dicke theory, maybe one that's more or less stretchy, and that would obviously change how that bowling ball, our planet or star, interacts with it.
That's a fantastic analogy. You really got it.
Hmm.
Now, shifting gears a bit, Einstein frame is essentially a mathematical framework that physicists use to make the equations in these modified gravity theories a little easier to work with. Think of it like a magnifying glass for a complex map, helps you focus on certain details.
Right, but like any tool, there are probably limitations to using this Einstein frame, right?
Absolutely, yes. While it's really helpful for certain calculations, it can also hide some of the finer points of these modified theories. It's about finding the right tool for the job, basically.
So it's like using a filter on a photo might make some aspects clearer, but you might lose some of the original image's richness and detail.
Exactly. It's a trade-off. That's why it's so important for physicists to use multiple frameworks, multiple approaches to really tackle these complex problems. They also work in the Jordan frame, which you can think of as like the unfiltered version to continue your analogy.
Ah, so it's this constant dance between trying to simplify things to make them manageable and trying to capture the universe in all its messy, glorious detail. And both think the universe likes to throw curveballs in there just to keep things interesting.
Without a doubt. But that's the thrill of it all, right? It's about constantly refining our tools, our understanding, pushing those boundaries to get closer to that ultimate truth of how gravity really operates.
Okay, so we've got these different ways of looking at gravity, different frames of reference and tools like FeynMG to help physicists wrap their heads around it all. But, something that really intrigues me is this whole idea of modified gravity. It's not just about like explaining away dark matter, right? There's this sense of, dare I say, possibility to it. Like if we could somehow tweak the dials of gravity, maybe we could unlock some really incredible things.
You're definitely tapping into something that gets physicists excited about modified gravity. It's not just about, patching up the holes in our current theories. It's about, well, the potential. The potential to uncover completely new and unimaginable technologies. I mean, if we crack the code of gravity, who knows what we could achieve?
Exactly. It's like in science fiction, you always see warp drives and artificial gravity and all sorts of mind-bending stuff.
hmm
Is that really just fiction? Or could this kind of research, this modified gravity stuff, could it actually lead to those kinds of breakthroughs?
Well, I'd say we're a ways off from warp drives at this point, but the pursuit of modified gravity does open some really tantalizing doors. Like one concept that gets a lot of attention is the idea of manipulating space-time itself, creating shortcuts, like wormholes, as they're often called.
Now, that would be a game changer. Imagine zipping across the universe in the blink of an eye. But let's come back down to Earth for a moment. This paper, it mentions something called kinetic mixing in the context of modified gravity. It sounds kind of like a physics term for a really high-energy dance battle or something. What exactly are we talking about there?
Actually, that's a pretty good analogy. Imagine you have these two groups of dancers, right? And they each have their own unique style, their own rhythm, normally just do their own thing, right?
Like two separate acts in a show.
Exactly. Now imagine the music changes, things get a bit funky, and suddenly those two dance styles, they start to blend, they start to influence each other. That's kind of what's happening with kinetic mixing.
So instead of two separate dances, we get this, like, fusion happening.
You got it. In the realm of particle physics, each particle, it has an associated field. It's like this energy field that, permeates space. Kinetic mixing happens when those fields start interacting in unexpected ways, like they start sharing energy and momentum.
Okay, so it's like our dancers are now sharing the dance floor. Their movements are getting all tangled up.
That's a great way to visualize it. And this mixing, it can have some pretty wild implications for how those particles and the forces they carry, how they actually behave.
So how does this kinetic mixing play out, specifically in the context of modified gravity? What are the particles involved in this cosmic dance-off?
In this case, the main players are the graviton, which is that hypothetical particle that carries the force of gravity, and something called a scalar field.
A scalar field.
Yeah, scalar fields can be a bit tricky to wrap your head around, but think of it as like a property that exists everywhere in space, like temperature, for example.
Gotcha. So we've got the graviton, our force carrier, and this scalar field, which is kind of like a background property of space itself. So how do they interact?
Well, that's where the kinetic mixing comes in. In these modified gravity theories, the graviton and the scalar field, they can actually exchange energy and momentum. They start influencing each other's behavior.
And that has consequences for how gravity itself functions.
Potentially, yeah. This interplay, it could impact things like the strength of gravity, its range, even how it interacts with other particles.
Wow, so we're talking about the potential for some really fundamental shifts in how we understand gravity then.
Oh, absolutely. It's kind of like finding this hidden link between two parts of a machine that you thought were totally separate, and suddenly you realize that, tweaking one can have these ripple effects on the other and lead to some really unexpected outcomes.
And this is where FeynMG comes in, right?
Yeah.
It gives physicists a way to model these incredibly complex interactions and see what happens, see how it all plays out.
Exactly. Tools like FeynMG, they're like powerful microscopes, letting physicists zoom in on these interactions, test different parameters, and see how the behavior of gravity changes when you throw something like kinetic mixing into the mix.
So we've gone from bowling balls and trampolines to like particles doing the tango.
Yeah.
It's amazing how these, complex physics theories can actually start to feel, well, almost relatable when you put it that way.
That's the beauty of a good analogy, right? But you're right, at their heart, these theories are all trying to get at something so fundamental about the universe, how gravity, this invisible force, how it shapes everything around us.
And what I find so fascinating about this whole area of research, these modified gravity theories, is that they suggest that maybe, just maybe, we don't have it all figured out yet. Like there might be more to gravity than we currently grasp, and that just it opens up so many possibilities.
It's like stumbling upon a hidden room in an old house, a house you thought you knew every nook and cranny of, and suddenly there's this whole new space to explore, full of potential, full of the unknown.
And sometimes you need a new set of tools to explore those uncharted territories, which is where FeynMG comes in. But this isn't just about, physicists getting their hands on some fancy new software, right? There's a bigger picture here.
Oh, absolutely. This kind of research, it has the potential to completely revolutionize how we understand the universe, our place in it. It's about pushing those boundaries of knowledge, exploring the fundamental laws of physics that govern everything. And I mean everything, from the tiniest particles to those massive cosmic structures, galaxies, everything.
It's like we're trying to piece together the universe's instruction manual.
Right.
And every new discovery, every new tool like FeynMG, it brings us a little bit closer to, cracking that code.
Exactly. And just like when we figure out, electricity and magnetism, look what happened. It led to this incredible technological revolution. So who's to say what practical applications might come out of a deeper understanding of gravity? New energy sources, maybe? New ways to travel, even? New ways to communicate across, well, unimaginable distances. I mean, the possibilities, they really are mind-blowing when you think about it.
It's pretty inspiring stuff. But for someone who might be listening to this, someone who's not a physicist, what would you say is the key takeaway? What's the message we want to leave them with today?
I think the message is pretty simple. Never stop questioning, never stop exploring. The universe is full of mysteries, and it's our curiosity, that drive to understand, that's ultimately going to lead us to the answers.
And sometimes those answers, they just lead to even bigger, more exciting questions. And that's what makes this whole journey of discovery so incredible, right? So to everyone listening, next time you look up at the night sky, remember, there's still so much we don't know about the universe, including the very force that holds it all together. But thanks to brilliant minds and cutting-edge tools like FeynMG, we're getting closer to unraveling those cosmic mysteries, one equation at a time. Until next time, keep exploring the depths of knowledge with the deep dive.